Hey guys, and welcome back. In this video, we'll be covering about interpolation. So basically, actually I have the introduction on the next slide. So suppose you have some known data points. So we given exact points of where those data kind of maps out to, and you wish to predict what other data points might be, right? So how can we do this? So this process is what we call an interpolation. So for example, if at time 1, some object has traveled 2 meters, and at time t equals 5, it was at 10 meters, then you could try to guess where it could have been at, say, t equals 3, right? So how would you do that? There are many ways of doing this mathematically, but what we can do is use Python functions, actually NumPy functions, that provides those interpolation solutions. So we can use interpolation to estimate distance, and this can be done using some of the Python libraries, right? And so the very first approach for interpolation is linear interpolation. So we assume that all the points will have a linear relationship in different segments. So it assumes that the data follows a straight line between adjacent measurements. So that means even though it might look like an exponent, what we can do is try to join those dots line by line. So if these two endpoints are our points, then we draw a line in between and say at time where we want to guess, we look at where those line crosses, and say that is the value at that time that we get. Okay, so that's the linear interpolation. So this assumes that the function between the 2 points is a straight line like this. Because we have very small example, it could have been like a curve like this if we have more points, or it can be the other way, or we can have some other weird lines going in between. But linear interpolation, just say draw a straight line, and if, say, for example, x equals 3, then where it crosses the line through, map it to the y value, then that's going to be the value. Okay. So find the equation of the line that passes through the 2 points, and then we put the values on it. So how do you find a point in between, say, x equals 2, like this? Then what we need to do is just go up straight and see where it crosses the y value on the graph. So here, in this instance, it's going to be 4. So for these 2 points, say at 1, 2, and 5, 10, that's what we had before. Or maybe at x equals 2 seconds, it may be traveled 4 meters. X equals at 3 seconds, it may have traveled, say, 6 meters, and so forth. So that's how we're going to guess what those points may have been using linear interpolation. Okay, so how do we do this? Of course, we can use these mathematical formulas to solve this, but those are already implemented for us in the NumPy library, right? So NumPy module provides this interp method where you provide discrete data points x, xp, and fp, and returns a linear interpolant value at x. Okay, so let's give that a go, implementing this one. Okay, so linear interpolation. So this code is the same as the one that you see here. So what's happening in the code? Let's have a look at it first. So we have x points. So these are our known points, and we're just going to generate 2 times pi between 0 to 2 times pi. We're going to have a 10 exactly spaced points. Okay, so the lin space provides us from 0 up to 2 times pi equals space of 10 points. Okay, and then y is going to be the sign of those x points. So that means we're just graphing the sign at these particular points. X values are going to be lin space 0, 2 times pi of 50. So this, we have the same range from 0 to 2 pi, but what we want to do is interpolate 50 points. So here we know 10 original points, and we have the y points, but here we're going to try to guess 50 points. Some of them will overlap, but 50 points to see where they might fall down. Okay, so the y value is going to be interpolated using our x values. Okay, from the point pairs of x points and y points. So those two are our known points, what we have, and this is what we want to interpolate using these points. Okay, and we're going to plot it to see how they look like. Basically, our original points are going to have the O marker and then we're going to have our interpolated points is going to have a solid line with an X marker. Okay, so let's run this. Where's my graph? Oop, 1 second. I forgot to turn off something. Subplot 1. Yeah. Okay, I'll run this. Okay, here we go. So this is the points that oops, I was supposed to have 10 here. Wrong graph. Ha ha ha. Okay, so so this is the graph where these blue dots represents our original points, and these, is it? Yep, blue dots are original points, and these crosses are our interpolated points. So this is how it's being interpolated from based on our blue original dots. So it's just making assumption that these points are connected by straight lines. So our interpolations are all just along the lines. Okay. So if we want to improve our accuracy, obviously we will need more data points of original. So we can easily just chuck in 100 like this and run it. Then it's going to be more accurate because now we have 100 original points, and each point we're going to draw an interpolation in between. Okay, actually our numbers should be greater than our original points to overlap properly. So that is described here. So if we only given 10 original points, or say very small original points, then linear interpolation may not be very accurate, but it does capture some of its characteristics. So if you assume that this is our more likely curve that we're supposed to get, then this one might have quite an error in between. So a linear interpolation, very easy to do. However, if you don't have sufficient original points, then our interpolation may have large error. So in order to minimize this, we can have higher ordered interpolations. For example, like a cubic. So a cubic spline interpolation is made up of segments of cubic polynomials. So between each line, we're going to use a cubic equation to model how that line is supposed to look like, whose gradients match up at the measured data points. So these cubic polynomials are continuous up to their second derivative. Yeah, so it's going to be using 3 different points to find out what the curve may look like. Okay, so we can achieve this using a library called SciPy. So it's a scientific Python library. So let's have a look how we can do this. Again, if you haven't got this installed, just go pip install SciPy, then that's going to give it to you. Okay, so let's have a look how to implement this. So this is the code using SciPy. So we're still using NumPy to handle arrays, but we're going to be using SciPy to do the interpolation. So what we have here is exactly the same. We have the x points and y points of our original points of 10. And then we're going to have a splines. This is using the SciPy's interpolate. And then we're going to have a spline representation of x points and y points. And then x values are we're going to create the points that we want to interpolate. And so this is our 0 to 2 pi using 50 different points. I should have arranged this nicer, so let me do that. Ta-da! Yeah, so this is creating our original data point. This is to estimate what values might have been in the other points. And then these two lines are our interpolations, cubic interpolations. So spline interpolation, so first we plug in our original x and y values. So the splines will interpolate using these points. And what we need to do is now generate our interpolated points using our x values. So we pass in x values and our spline as an input to SPLEV method of the interpolate. What this method do is now trying to use cubic interpolation to find out what these values supposed to have its corresponding y values. So here it's going to output our y values. Then we can plot the same way. So these two lines are the ones that resulting of using the interpolate method. All right, so let's have a look at that. So that's linear interpolation. So we have a cubic interpolation. Let's move this down here like this. So that's the setup. These two lines are our interpolation. Interpolate using the original points and map out onto our suspected points of interests and then plot it. So let's plot this guy, run it. And so now this is the interpolation that we get using a cubic spline interpolation. So compared to our linear one, as you can see, this one, because we know the sign graph, probably looks more smooth and more accurate than using a linear interpolation. Okay, and so this is the result that we just saw. So probably using cubic, if you know the graph has smooth lines, this is going to give us a better fit of how the line should look like. Okay, so there's another way of doing this using an interpolate. How do you read this? Interpld method. Let's say that. Okay, basically, what has changed is highlighted in red. So here we have the setup, but now we are creating a function. Okay, interpolate.interpld x points, y points, and we want to use cubic. So here, if we change this, we can change to linear or some other methods, but cubic is what we want to use, and then we can generate y values using this f function. So in that sense, this might make more sense to use rather than doing the spline. Okay, so let's give that a go. So create a function that uses our original point using cubic for interpolation. So this function, if I chuck in some values, is going to give me the interpolated values. So this one actually essentially produces the exact same result as before, like this. Okay, so this one, as you can see from our previous one, has exactly the same result because it is still using the cubic. So we can easily change this to linear and run it. Then what we're going to see here is the same linear interpolation that we had before. Okay, so this one allows you to specify the mode a bit more explicit and use it as a function that you pass in a bunch of numbers, then it's going to spit out the numbers corresponding using the function that you created. Okay. All right, so that is the basic interpolation using linear or cubic. The implementation is quite straightforward. We use NumPy to store arrays and SciPy to do the interpolations for us. So now let's move on to a 3D plotting, right? So in 3D plotting, what we have is, okay, let's just quickly look, kind of like this, a 3D dimensional graph. Okay, and these are all also supported in the Matplotlib module. So this is useful when you need to display the surface or when you have two variable functions, right? Basically, if we have a function of x, then this will input a function of x and y, two variable functions. So these will generate all the surfaces for us. Okay, and this is actually quite straightforward to use. We do have to use some libraries like this. So please have these at the top to use it. And it just looks like the code is quite simple to do so. So let's have a look. Oops. Okay, and what we're going to do is we're going to use this plot data function. What this do is if we chuck in some values x, y, z, then it's able to plot us the surface. So here we are using a plot surface. If you remember the previous video, there were a lot of different type of graph that you can generate, and plot surface is one type of graph specifically for graphing 3D types. So we'll be using this function to draw this graph from our interpolated data. All right, let's have a look. So that's the function, and ooh, so many interpolates. Yeah, let's separate them a little bit. All right, so this code here is this code here, right? So I just chuck it into a function. Okay, so what's happening here is our original points are x points and y points, and basically what we want to find is the corresponding z point when you're given x and y. Okay, and what we want to do is create a mesh grid of x values and y values. Okay, and essentially the z values are going to be the sine of x value plus cosine of y value. So you can see that it's kind of like a water ripple kind of surface that we're trying to generate. And then what we're going to do is plot this. Okay, so if we plot this, so this is our original plotted data. If it ever gives me this graph. Here we go. Yeah. So one thing you can do with these 3D plots are that you can drag this around to change the view as you wish, like this. Okay. So then you can like make them flip around and change the viewing angle. And when you press save, that particular viewing angle will be saved as an image. Okay. So make sure you find the best angle for you to do. Okay. Anyway, so this is going to be our original data we'll be using. Okay. So we are given these data points to work with and trying to do some interpolation to make our surface look nicer. Okay. So that is our goal. Okay. So now let's have a look at the linear interpolation in 3D space. Okay, so what we need to do is we're going to use the interpolate interp 2D. So interpolation in 2D space when we're given a two-dimensional data set. Okay, and we can specify the kind. Okay, so let's do that. We can hide this guy. Okay, so this is our interpolation stuff. So up here, this is our original points that we have seen before. It ranges from -5 to 5. We create a mesh value, and then we populate the z value using the sine and cosine. Okay, so this is our original points. And now here underneath is where we generate our interpolated functions. So here f is going to be our interpolate interp two-dimensional points. We pass in our original x, y, and z values. So these are our original points. Okay, and we say that kind is linear, so kind determines what kind of interpolation we're trying to do. Okay, so our new x points, what we want to do is have the same range so that we map it onto the same area, but our guess is going to be in increment of 0.1. So that means we're trying to guess more points in between and see what they look like. Same with the y. So we create a mesh out of these first, and then a new z value equals, we use the function now. So this is where our values, the z values, gets interpolated from the function that we created up here. Okay, so using original value, we create an interpolation function, and then once we pass in our x and y points, it will spit out our z points. Okay, then we can plot our new x value, new y value, and new z value here. So let's run that. And once this successfully plots, and this is what we get. So as you can see, we are skipping through 0.1 range, so our mesh is more tight with less gap in between. So we had a blocky one. Okay, so this is the interpolated one. As you can see, because it's a linear, it has a very sharp edges. Okay, so let's have a look side by side what it looks like, which is in your lecture slides. So this is our original point, and this is our interpolated point. So as you can see, it is doing well. It is looking very similar because it's using linear, but it is capturing a bit more details than this one because well, it is not capturing more details, to be honest. To capture more details, we do need more original points, right? Because linear is just drawing a straight line between points. So as you can see, linear interpolation may not be best fit in this instance. So let's try a cubic one. All you have to do is, from the previous code, change the kind into cubic. Okay. Cubic. So I'm not going to change anything else. But if I run this, the generated graph is looking like this. It's very curvy, and probably this is what we expect using the sine and cosine values that we have used, right? So going up and down like this. Okay, so that's good. So let's have a look how it has displayed. Oh, I updated variable values here. I will update this. Okay. So this is our linear interpolation, and this is our cubic interpolation. So you can see the difference that cubic will try to use multiple points to smooth out how it's supposed to look, whereas linear is just joining. So depending on how those points are related, because we know that sine and cosine will generate smooth lines, this is better fit. But sometimes linear may be a better fit, especially if the points have a linear relationship. So that's pretty much it on interpolation stuff, really. You can either work in 2-dimensional or 3-dimensional, but we can do interpolation in both using these. If you would like to see more notes on 3-dimensional interpolations, please see this note. Otherwise, we will stop here. I'll see you in the next one. Bye-bye.